So hi everyone. In this video, which will be the last video that will play with our example, we are going to consider more floors. So a tower with more than just 2 or 3 floors, 2 extensions or 3 floors, and we are going to see how the genus evolves and how the number of rational functions, rational places evolves, and that will kind of regretfully show us that our tower of the function fields, the example that we have, if we kind of recursively define the function fields using it, won't get us good code, not at all. But then we'll see a much better tower without yet analyzing it, just like looking at it in a somewhat analogic way to what we did so far, somewhat informally. And it turns out that that actually is an example of a optimal tower, as it's called. Okay, so as I said, we're going to consider now more floors using our defining equation. So if you remember so far, when we had 3 floors, the kind of geometric picture was that above the place at infinity, there is only one place, the ramification is 2, and so we denote it also as infinity, and that proceeded on and on. Above 0, again, the same spirit, same as -1 and 1, you get ramification, total ramification, but ramification is total ramification when n equals 2. And like the prime divisor above 0 behaves in a sense like 0, namely the new coordinate is actually 0 at that point. And -1 and 1 also kind of converge to 0. Everything here has ramification 2. Above 2, you had 2 places, but the coordinate, the new coordinate was 1 and -1, so you kind of continue to evolve as if you were here in a kind of a recursive manner. That's what's nice about working with the same defining equation, because you can infer what happens and prove it afterwards if you want, kind of by induction or something, as it happens throughout. But at least informally, and you can convince yourself that this is what happens. And -2 was the one thing that worked well, namely branched out and out, and didn't cause ramifications. -2 had above it a prime divisor 2 and -2, and 2 look like this. So here we have a 0 and a 0 throughout. But -2 above it again has a 2 and a -2, and that branch will kind of live, like this will branch forever. So because we are computer scientists, we know how to write it using like a kind of a finite automata or something. So you have like a state for every field element, like the possible coordinate, new coordinate, and you see that infinity goes to infinity, 0 goes to 0, and so forth. 1 and minus going to go to 0, -2 is kind of keep generating itself in 2, which in turn generate 1 and -1, which in turn generate 0, and then it gets stacks like that, and so forth. So really that's all you need to know. Maybe also some information about ramification, but that's essentially all you need to know. You don't really need to draw this thing, you can draw that thing. Well, it's hard to draw this thing unless you kind of build up some flows and you get the sense of what's going on. Okay, but we have this behavior. And if you just think what happens in the next layer, like using that or using that in your imagination, you'll see that, as I said, so you'll have this branching, but that branching will be like the better branching that keeps going on. So -2 will be your favorite prime divisor. Okay, so if we denote by little n of I, the number of rational prime divisors in Fi over F5, in the ith floor, then you can easily see that the number of points increase by an additive 2 at every layer. It starts with a 6, 5 plus 1 for infinity, and then every time you move up, you get 2 more places. And this is really just because 2 of the places split to 4 places. So instead of 2, you have 4, and the remaining stay the same. So it adds up to 2 every time. And so ni, number of rational points, is s plus 2i. Right, so if you want to construct a code with some given n number of block length n, then you would need to choose I to be roughly n over 2 or n minus 6 over 2, which is quite large. You need to go and extend your you need to extend like something like n floors or n over 2 floors of a tower, you prefer this to be something like log n. You'll see. Anyhow, what about the genus? So I actually don't know, I didn't kind of verify what is the genus, but I know to give a lower bound on it. That's easy. So we know that according to the Horowitz genus formula, GI is 2, that's the extension Fi over Fi minus 1. So GI is 2 GI minus 1, and then you have, minus 1 plus half the degree of the different. I mean, the formula looks like that, but you see this is 2 and this is 1. So all in all, you get what I said there. You move the minus 2 divided by 2 and so forth. And the different, given like that, generally, we said that every prime divisor that ramifies contributes its degree to the different. And in particular, if I want to lower bound the genus, just to show you something, then it's enough to consider just a subset of the ramified places that I can eyeball. Okay, so in particular, the degree of the different is at least the number of places that ramify in the previous level. And in our case, it is easy to see that above the rational prime divisors, not like the weird one that we had like x squared plus 2x plus 3 or something, just above the rational prime divisors, you always have like 2 more divisors that ramify. So what are the prime divisors that ramify here? Well, initially you have this 4, right? And then you have these 2 gives you another 2. And then these 2 give you another 2 and so forth. So if you think about how many ramified places do you have, and put that, so you have 4 plus 2i in the ith level, because you start with a 4 and then every time you get 2 i's. And so plugging this back into the degree of the different, you get the GI is at least 2 GI minus 1 plus half times 2 plus 2i, whatever. So it's 2 GI minus 1 plus I. And solving using the G0 is 0, you get the GI is exponentially in I. So it's 2 to the I plus 1, maybe minus I minus 2, but generally it's 2 to the I plus 1. And that without accounting even for the ramified places that are not irrational places, which do affect the difference. But to summarize, we have that the number of points goes like that, and the genus goes like that. And that's terrible, right? Because the genus increases exponentially, and the number in I, and the number of rational points increases only linearly. And if you remember, we know that the rate plus distance is 1 minus essentially G over n. So you want G over n to be small, but it's not. It's actually in maybe floor 3 or 4, it already, this is larger than 1. So you get a non-meaningful bound whatsoever. Yeah, and that's that. I mean, just even accounting for the rational ramified places, you see that you're in trouble. I mean, that will happen. The question is, can you get the number of rational places to be larger than like linear in Y? You want in I. You want it to be also exponential in I. So I do want to show you another tower, which is related to what we have, but it's different. And that turned out to be a much, much better tower, an optimal tower. So let's consider the function field. Well, the constant field is F9, and you have x and y that satisfies the following relation. So it's y squared plus x, y squared equals x plus 1 over x. If you remember, we encountered that when we talked about Kummer's extension, because that is a Kummer extension. It's a very simple extension. It looks like this, and it satisfies, the Kummer criteria. You have polynomials over polynomial. They are reducible. Maybe this is reducible or reducible. It doesn't matter, but you can factor it out. It depends on the field arithmetic. If minus 1 is a square, this is also a degree 2 extension, so there's no issue with. It's called a tame extension because there's no issue with characterization, the characteristic dividing the ramification index. Right, the characteristic is free, and the ramification index can be at most 2. So you're fine using like Dedekind's different theorem in order to compute the genus using Horowitz genus theorem, and everything is nice and fairly easy. And if you play with it, and actually that's a fantastic exercise to do. So if you play with it, well, I'll show you in a picture what happens, but okay, maybe let's do it right now. You'll get the following picture, which I urge you to do. So what's going on here? So we're talking about F9. So here what happened is that I took a representative. I'm not sure exactly how I chose it. Right, so what I'm doing here, delta is so I think I took, so I forgot it was a long time ago. I think I took F9 to be, so I represented F9 as an extension of F3 of degree 2, and so I had some irreducible polynomial in mind. So maybe I took it to be like, something like that, divided by, and then if I know myself, it should be this. Let's just assume that this is irreducible. Because it's a degree 2, it's enough to check that it's doesn't have a root, and it doesn't have a root in F3. Because 0, when you plug it here, you get 1, and when you plug -1 or 1, you get 2. Yeah, so that's the irreducible polynomial, and I think delta here is like I, like the square root of -1. And this is a nice multiplication table for you. Right, so not multiplication, like not just multiplication. It's a table that will help you calculate. So these are all the possible values of alpha as an element in F9, and this is the squares. From here, I can actually even verify that what I wrote is correct and so forth. This is the right choice. Yes, for example, if you take delta squared, you get -2, which means delta squared plus 1 is 0. Sorry, delta squared is 2, so delta squared -2 is 0, which is delta squared plus 1, which is 0. Good, that's the right choice. And I also computed 1 over alpha because we need this, right? If you remember, we need that thing. And actually, we need that thing because y squared is x plus 1 over x. So anyhow, this is a table that will help you to calculate in F9 in this particular representation. And if you do that just using the fundamental equality trick and the other things that we saw, you'll get this behavior. So above infinity, there is only one place that totally ramifies, and its local parameter is y over x. So you can call it infinity if you want. And above 0, you again have only one place or prime divisor that ramify xy is going to be its local parameter, and same for delta and 2 delta, but they will go to 0 in a sense. Now 1 and 2 behave differently than 0 delta, 2 delta, and infinity. They do branch out, so no ramification in particular, but they branch out to element, so 1 branch out to element here, and 2 kind of keeps generating itself, and 1, kind of similar to what happened before in the example of the elliptic curve, like y squared equal x cubed minus x. But now the amazing thing that happens here is that these other 4 elements, right, you have to have 9 altogether, 10 altogether, I'm saying 10 because of infinity. So these 4 elements actually splits completely, and they split among themselves. So delta plus 1 generates itself and this thing. And delta plus 2 generates delta plus 1 and this thing also. And so forth. So they will keep, if you look at it for a second, you'll see that they keep generating more and more rational places, also not contributing ramification, which is great for the genus calculation. And I'll leave it to you to prove that the genus is 1. That's obvious from the genus, because this is a Kummer extension, you had a very simple formula for the genus. But at the next layer, what you'll see is this thing. Right, infinity goes to infinity, so it will keep going to infinity. And yeah, interestingly enough, 0 goes to infinity, but that's actually another infinity. I'll let you figure out what I mean by that. But that other infinity happens to go to infinity at the end, so anyhow. And 1 splits again to 2, and as I said, it splits to 2 to delta and 2 delta, but they go to 0, which at the end goes to infinity, but it doesn't matter. The only thing I care about is the shape of the thing, not the elements that are written there. 2 will split nicely up to this point, but then from here on that will be 0 and 0, and then that will keep splitting a little bit, and that's less. And yeah, these two are terrible to begin with, but these four are amazing because they generate like 4 to the I rational prime divisors at level I. So, if you believe me about that, then you see that the number of rational places is at least, just accounting for this, is at least 4 times 2 to the I, because you have 4 places that every time multiply themselves. And the genus calculation is actually harder, but you should trust me that the genus is 2 to the I plus 1 minus I plus 2. Actually, I don't quite remember how I got this number. At the end of the course we'll see, but definitely it's true that because of the ramified places here only even, you'll get this number, and I guess what I'm saying here is that there are no other places that ramify, but yeah, I should trust myself here, but I don't remember. And therefore, if you think about it for a second, look at it, so G over N approaches 1/2 as I goes to infinity. Right, so this means that, if you want to construct a code, and that's an important remark now, with block length n, then you just need to set like 4 times 2 to the I to be n, so I is roughly log n, so log n layers. So you get enough points, and the genus won't, the genus will be like, asymptotically be like half the number of rational points, right? Because here, this is like 2 times 2 to the I, and this is 4 times 2 to the I, and this doesn't matter asymptotically. So the GOPA code that we initially, lecture 5, we defined, instantiated with this particular function field, or like the function field that appears at the end after log and layers, gives you rate and delta whose sum is at least half, maybe minus little of 1 because of this I. And over F9, these codes turn out to be optimal GOPA codes. Generally, if you remember, I told you that the best thing you can get is something like square root of q minus 1. So rho plus delta will be at most. This is an impossibility result. So you can never go, like 1 minus that. You can never go, you can never be as close to 1. This gap will always be there if you're working with alphabet of size q. And in our case, q is 3, so q is 9, so square root of q is 3, which gives you a half here. So actually, these are optimal GOPA codes, and we'll talk about this particular code later on. Turns out that the exact same code work if you replace F9 by any prime power, maybe a power of 2, or maybe an even power, I don't quite remember actually now. And the characteristic should be larger than 2. Okay. Yeah, good. So that's it for now. And then in the remaining of the course, what we are going to do is to start developing the machinery that will enable us to prove these great results that we just used, like Kummer's theorem and Horvitz's genus formula and Dedekind's theorem. And the fourth thing that we will do, which is the next video, which I'm also going to put online like that, the physical lecture will be later, is about normal extensions. So these are function field extensions in which the corresponding Galois group of f over E is normal. And it turns out that in this case, in such cases, you can say much better. You can also understand the ramification index and residual degree as some group size, some natural group size that we'll talk about.